So yesterday we learned that the velocity required to maintain a circular orbit could be described, let me finish this one thing real quick, could be described using this, right? Let's use capital R. All right, but that was specific to a circular orbit. All right, and so what Francis was saying, well, what if I want to get into an orbit, but not necessarily circular? What's the minimum velocity? Okay, so that was the question to pose. Yes?
I was saying, isn't it entirely dependent on how far you, like, how long your orbits be, but, like, couldn't it go technically to infinity? Or until you...
Yes. So yes, it's 100% dependent on where you launch from, and yes. Just as this is, right? So if I want my orbit to be at radius r, that radius is going to determine the velocity. Good? All right? So let's suppose that we've chosen that r, okay? And we're going to launch our projectile, our satellite, from that radius. And now the question is, what's the smallest velocity I can have so that it so that it stays in orbit? Okay? Well, you all know there's an upper limit, right? What's the upper limit? A lot of you guys are nodding. What do you got here? The escape velocity, right? So if the velocity is too big, it's going to escape, right? Okay? What's the problem if the velocity is too small? Instead of it escaping, what's going to happen? It'll hit the planet, right? Okay, so the other variable, there's two variables. There's the orbit radius and, well, the gravitational pull for sure, the radius of the planet, right? Because if the planet's really big, you've sort of got a bigger target to hit. It's a little bit sloppy, but you guys see that would be an issue? Okay, so let's see if we can use that. All right, so check it out. So here's our planet, right? Okay, and it's got a radius of, let's call that little r, because that's going to be our smaller radius. All right, and we're going to launch our satellite from over here. I'm going to just use a little star to represent our satellite or whatever it is that we want to put into orbit. We're going to launch that from a radius of big R. Cool? Now, for simplicity's sake, let's assume that we are launching it in a direction that is perpendicular to that radius. Okay? Which is what you would do if you were putting it into a circular orbit, right? That's by definition of circular orbit. Follow? Okay. So, our limiting factors, we need to make sure that it doesn't hit the planet, right? Okay, well, do you guys agree that if it clears this point, then we're good? Right? So I think David yesterday had said, well, let's think about that point, and that was a great intuition. So let's imagine an orbit that just barely, boop, kisses the planet, right? That's our limiting factor. As long as our velocity is big enough to get us around that point, then we're in good shape, right? Does that jive with everybody? Okay, cool. So we need to make sure our velocity is bigger than that. So this right here is enough for us to figure out the shape of our ellipse. It's basically to figure out the length of our semi-major axis. Okay? So I'm going to take this and I'm going to recreate this drawing down below. I think you're 100% right, and I'll be honest with you, I don't know that I had processed that. All right? So this is an elliptical orbit, right? Okay, and what do we know based on Kepler's laws? What do we know about our two foci? One of them is not the planet, but the center of mass of the planet, right? Okay, so this is one of my foci, right? We'll call that F. And then the other one is somewhere out here in space, right? You guys agree? All right, well, check it out. I know that this distance is r, and I know that this distance is capital R. Right? If I add those two things together, doesn't that give me twice my semi-major axis? Aha! Hello? David, you had a hand up?
No.
Okay. Everybody good up to there? All right. So, how do we make this happen? Well, yesterday we learned some important stuff about energy, right? And when Francis asked the question yesterday, that was the first thing I said. I said it's got to have something to do with the kinetic energy at that beginning point, right? Okay. So we learned three things about energy yesterday. Okay. We learned something about gravitational potential energy, something about once you know that gravitational potential energy, what the kinetic energy is, and finally what the total mechanical energy is, right? So this was just that equation, right? G times the mass of the planet times the mass of the satellite, all divided by, divided by R at that point, sorry. Good. All right, and then what did we learn about the kinetic energy? It's negative 1/2 of this, right? Follow? All right, and then what do we learn about the total energy? That's negative. It's negative K. That's the same as positive U over 2, right? Does that ring a bell? Question, Ethan? Are you just stretching? You good? All right. So, we need to ensure, sorry, just lost my train of thought here. Smart board. There we go. Oh, go ahead. Right, well, so what we learned yesterday was that, so remember there was that initial confusion, and I said, well, these are only true if you're in a circular orbit, and then a minute later I was like, that's not right, it works even if the orbit is elliptical, right? Okay, but what do? You replace R with A, aha, and we know what A is. Follow? So in order for this to work, our E, our total mechanical energy, has got to be equal to that gravitational potential energy divided by 2. Right? At this point, don't you guys agree that there's some gravitational potential energy? And that's determined by your launch height. Right? So to complete the orbit, so let's call U the gravitational potential energy at launch point. Well, your mechanical energy then needs to be positive U divided by 2. And so I think you ought to be able to work backwards then and figure out what the velocity is that would give you the kinetic energy to allow you to correspond to that amount of total energy. Make sense? Why is your total energy not just, again, you're on deck. Because, well, so what are the two types of energy we're talking about? Potential and kinetic. So talk to me about potential energy. Why do we have potential energy? Right, so it depends on gravity, but it also depends on the distance the two objects are apart, right? So the idea is the satellite has gravitational potential energy because it's removed from our center of mass, right? So we got potential energy, right? What other type of energy are we concerned about? The kinetic energy. Why do we have kinetic energy? Yeah, we want this thing to move, right? We want to put it in orbit. It's gotta, cool. So it doesn't just have potential energy at that point, right? Right, but and so our goal is, in order to put it into orbit, it needs to be moving, right? So the idea is once you determine this potential energy, and you determine the length of your semi-major axis, that determines how much energy you need to keep the thing in orbit. Okay, jumping back to the notes real quick from yesterday, was I smart enough to open them? I was not. Give me 1 second to open those up. Smart board. Chapter 13. There we go. Give me 1 second. And I think to be honest, I think I glossed over this a little bit yesterday. Thank you for being patient. All right. So while this is loading, are you good with why it has both those types of energy? All right. So remember, you guys, what this is all hinging on is, again, something I think I didn't do a great job of stressing yesterday. The total energy of a satellite is dependent on, well, the masses of the two objects, but fundamentally the length of the semi-major axis. Okay, and there's a sliding here. Holy moly, why is it going so slow? Maybe because I have like a billion things open right now. So, you like this? Which one? What do we got? What is it? Man on a scale. Really? One more. Somewhere. Did I pass it?
We do a lot of stuff.
Yeah, we do a lot of stuff. Well, this is like 2 days of notes too, right? Wild. All right, almost there we go. Okay, so and I totally glossed over this yesterday, but look. Oh, stupid technology acting in a predictable way. All right. So remember, the energy of the orbit depends on the semi-major axis. Depends on the length of the semi-major axis, and I glossed over this yesterday. All of these drawings here have the same semi-major axis. So these are different orbits around some, whatever, some central body. Okay? And they all have the same total energy because they all have the same length of semi-major axis. In other words, if you measure all the way across any of these shapes, they're all the same. Does that make sense? Good? All right. So what I'm getting at is that once you've determined your orbit height, like where you want that orbit to start, and you know the radius of your planet, those two things determine the length of your semi-major axis, and therefore the energy, and that therefore indirectly is going to determine your kinetic energy. Make sense? Yes.
Isn't the circular orbit velocity equation derived from the energy equation?
No. The circular orbit equation is derived from Newton's laws. Where was it?
So does the substituting A for an ellipse work?
Did I pass it? This way?
Oh, no, all the way.
All the way? Thank you.
It's on that slide. There you go.
No. Oh, here it is. This is it. So all you're doing is you're setting your force of gravity, Newton's laws, equal to the centrifugal force equation.
Yeah, but didn't you say that we could substitute A in for that as well to get the orbit?
For everything except for equations that stem from this guy. I think this is the only one that you can't do that for, actually.
Oh, really?
And I'll double check that.
Okay. I thought I remembered seeing it because so I was gonna ask, like, can you just substitute as
I think Patrick asked that, and then the answer is because it's for like perfectly circular orbit. So if you substitute an A in, it would just a perfectly elliptical orbit. So
Yeah. So the derivation of this equation, I don't know if you guys remember, we did that with some similar triangles and some geometry and algebra and stuff. It hinges on the fact that your motion is perpendicular to your radius, which is only true for a perfect circle.
Oh, okay.
Okay.
That makes sense.
So,
You can't just substitute A into the GM.
right.
Okay. That's not.
Yeah, good questions, guys.
What makes it able to interchange so that FC and FG can be equal? So like, how can Y?
The moon. Let's think about the moon for a minute. Its orbit isn't a perfect circle, but it's pretty close, right? Why? So the moon is going in a circle, right? So Newton's hanging out under the apple tree one day, thinking, I know that thing should go in a straight line unless there's a force on it. And then you realize, what's the force that prevents the moon from floating away? Gravity, right? So when I grab my B and I say, what's providing the centrifugal force? The answer is the string, right? So in this example, the tension is equal to the centrifugal force, right?
Yeah.
Okay. Here, it's the Earth's gravity that's equal to the centrifugal force on the moon, right? Because that's what's preventing it from floating away.
Yeah.
Cool?
Yeah.
It's just like we did all those problems about a car going around a circle, right? And it's like, the friction is equal to the centrifugal force. Or on the salad spinner or the rotor, the normal force is equal to the centrifugal force, right? So it's what's making the thing go in the circle. And in this case, it's gravity. Cool?
Yeah.
Alex, are you good?
Yeah.
What's up?
So that circular velocity equation, is that the velocity like launched from a point r distance away.
From the center of the planet or sun or whatever, yeah.
So that's what the r is.
Correct.
So if you want your radius of your orbit to be r, you have to launch it from that distance.
From that velocity.
From that, yeah.
Right, so
Yeah.
the r at which you, the radius at which you want it to orbit is going to determine the velocity.
Yeah. Yeah. And you have to, yeah.
Good? Everybody good? Francis, are you good? Is anybody not good? Is anybody lying about their state of goodness? All right, so here is my charge for you guys. So what we just decided in all of this, which screen was on? Too many windows. So what we just decided was that this velocity is dependent on this radius, and I'm guessing, although I haven't done the calculations yet, I'm guessing one other thing. What other thing do you think it probably depends on? Two radiuses and radii, if you prefer.
I think.
Yeah, we got the mass of the thing that's being orbited, right? Okay, so here's your job. So given r, the radius of a planet, and r, let's call it the launch radius, I guess. Do you guys know what I mean when I say the launch radius? Yes, correct. That is going to be the farthest point on the ellipse, correct. Launch, looks like lunch. Launch radius. And m, capital M, the mass of the planet. Planet, that is not at all how you spell planet. Find the minimum velocity required for any orbit, circular or otherwise. All right, and I've basically given you the tools. What big concept does it hinge on? Energy and conservation. That's their thing. Alex, what do you got?
We made the assumption that to make it past like the point that's on the other side of the planet that it's good. I don't know if we addressed this. If the big R were big enough, would it be possible for the elliptical orbit to hit like the side of the planet rather than?
No, again, because of conservation. Oh, wait.
Like really long, the ellipse would be almost a line segment.
I gotcha. Okay, so, all right. So let's suppose we found this velocity, all right? And just for simplicity, let's suppose it's 10 meters a second. Cool? All right, so what that means is 10 meters a second will just kiss this point on the planet, right? Good? Now, the only way that it could possibly hit the planet at a point other than here is if I launched it from here at a velocity slower than 10. Right? If I fire it at a velocity of 0, what if it's not moving at all and I release it? What's it going to do? It's just going to go and hit there, right? If I fire it this way at, say, 1 meter a second, it's going to go 2 meters a second. You see what I'm saying? And it'll get closer and closer to here until you get to 10, and then that's the magic point, and haha, now this is when it gets to that point. Okay? Does that make sense? Cool, you guys? All right, so that's an extra credit problem. I think that's the first extra credit I've offered you guys this year. Right? So we should decide on point values. You're not going to like it. Are you ready for this? Let's see how many people are in here. What should we do?
5, 20,
105.
100.
Hold on.
Times 30.
Divided by 0.0. Yes.
Divided by the number of people to get it right. Do your own work. All right?
Yeah, Shakespeare.
Follow?
Shouldn't it be the class size rather than the number of people get it right? Ooh. Is there a ratio there?
Yeah.
I'll go 30. That's cool. Class average is a little low right now.
Yeah, I was gonna say 15, but have more people get it right than our.
Oh yeah, right. Because if everybody gets it right, yeah. Do you know what? And if everybody gets it right, awesome. You know what? Oh. You guys think?
The ratios of people who got it right.
Wait, so I'm the only one that gets it right. I get 61.
So that's back to 30. 37.
Wait, so
What's up? So if you're the only one that gets it right,
what can you do tomorrow?
huh? Oh, you're like, due date. What should we should pick a due date.
Everyone band together with PTA 2 points.
You got some strategizing to do here.
Everyone themselves.
I also suspect that this could be Googled pretty easily.
Okay.
All right, so what do we got? How about that Thursday after break?
You have the extra factor for that you can just straight get it.
All right, cool, you guys? Yep, in terms of those givens. And if it's not possible, tell me why.
Oh, okay.
No.
So
What are we discussing here?
Oh, is it the prisoner's dilemma or not?
Oh, I gotcha.
It's technically,
Oh, yeah.
if you to both fail, then no one gets any benefit.
Right.
So I say we draw straws and 15 seconds. And then everyone else gets
But prisoner, no, yeah.
So to be clear, since this apparently is grown in stakes, to be clear, launch radius is this. Here's your planet. You're going to pick a point out here in space and launch it at a.
From the center or from the surface?
So the radius is from the center.
Yes.
And to that end, make sure you're careful doing the homework, because sometimes they give you the distance to the center and you got to tack on the planet. Or sorry, sometimes they give you the distance to the surface and you got to tack on the radius of the planet.
So R plus R would be total.
Yeah, so bigger plus the large.
No, this is big R
Is that from the center?
from the center of the planet. From the center of the
Yeah,
planet.
so just like the other one.
Just like
Bigger
that.
plus the large.
So both R's are measured from the center of the planet.
Technically greater than, if you don't want to technically.
Right, yeah.
Yeah,
Center of the planet is center mass too.
Center, yes, center planet and center mass. We're assuming uniform density. Or at least symmetric. Okay, cool, guys? All right, so thank Mickey for the boost in points, and Francis for a really cool question yesterday that I'm surprised I'd never heard before. All right, I'm curious to see what we get here. Like I said, I have an idea for how this works, but I haven't had a chance to sit down and figure it out yet. So, cool? All right, so chapter 13. I told you guys I would do some Q&A stuff. So why don't you guys dig out whatever you've got done on the 13 assignment, and let's see what you guys need to talk about. Sorry, I'm not ignoring Ethan. I'm finding my stuff. All right, yeah, what do you got?
51.
From the problems?
Yes, it's going to be the 3, 5.
So let me hold off on that, because we just finished those notes up yesterday, so I just want to do the first chunk right now, if that's okay. Let me take a look at it real quick, just I'm curious which one that is.
You want that in Newman vector notation?
Number 56, is that what you said?
51.
Oh, 51, okay. Do I want this in unit vector notation? Is that what you said, Marcus? This in unit vector notation?
I lied.
Okay. He was joking. So Marcus, 51 is actually, you need to figure out 51 before you solve this problem. Okay? Because, that might not be true actually.
Wait,
But 51 is all geometry. It's an ellipse, and you're given some distances, and from that you got to find the length of your semi-major axis and the eccentricity. So everything you need is, remember, your eccentricity is C over A.
I was getting the semi-major axis C.
Oh, wait a minute, there's no way it can be kilograms. That's a typo. It's got to be kilometers.
Well, that was.
Wait, is that a point? Point?
Yeah.
All right.
You already got
I
me?
couldn't get that number.
Okay. All right. Well, yeah. Let's move on to the current stuff. All right. Sorry. Yes. Kurt.
This may be something since I missed the beginning of the student, this may be something I think simple from covering it, but 11 on the other questions. I thought that
The concept or the?
just like the concept questions.
Oh yeah.
I think technically all equal because it's just totally dependent on. Oh no, that's for.
Yeah, so you did miss this. So I'll explain it real quick. So here's the idea. So here's the Earth, right? North Pole, South Pole, equator, right? So the idea is if you're standing here, then gravity's pulling you down, right? Everything's good. So if you were to stand on a scale, the normal force from the scale would be pushing up on you with exactly enough force to make your net force 0 to cancel out your force of gravity, right? Good. The problem is, if you're at the equator, aha. So your net force at the equator isn't 0 because of the centrifugal force. Follow?
Yep.
So we did a calculation the other day, figured out how much lighter you would be at the equator due to the Earth's rotation. And I don't know, does anybody remember what the answer was? It was like 0.1% or something. You know, I mean, it's insignificant, but it's it's a real definable number.
Smaller your period is basically what happens.
So the smaller your period is, the faster you'd be moving, and therefore what? The greater the centripetal force, how's that going to affect your weight, more or less?
More.
I think that it would have to be less, right? Because which way is your centripetal force directed? Inwards, right? So here's my centripetal force, that's the gravity, right? Normal force, right? Which of these forces do I need to be bigger? The gravity needs to be bigger, right? Because you need to produce a net force inwards to give you that centripetal force. So you get your centripetal acceleration. Good. So the faster you're spinning, the bigger the difference has to be between these, which is decreasing the normal force. Cool. Another way you can think about it, it's a little bit sloppy, but you know how we talk about centrifugal force, there's this feeling of being pulled outward. Again, it's just perceived, but it's there. But that sort of perception is that you're going to be lighter, right? Because you're being spun outward. It's sloppy, but if it helps you think about it, it adds up. Good. All right, what else, guys? 4 on the concept. Alex, what do you got? Can you hand up or no? What's that?
The extra credit, I think.
What do you mean, I think? Okay. Jacob, what'd you have?
I had number 13.
13. Concept or problem?
Problem.
Problem? Okay. Let me do the concept one and then we'll do the problem. Would you say 4?
Yeah, I could try to do it.
Well, let's take a lookie. Let's see. In the figure at the left, 2 particles of masses blah blah and blah blah are fixed in place blah blah blah. All right, so here we go. M and 2M if you are keeping score. This is concept question number 4 from chapter 13. Let's see. So it says if the distance between the particles, then in terms of d, where on the axis can a third particle of mass 2m be placed, other than infinity, so that the net gravitational force on it from the first 2 particles is 0. All right, so the idea is we've got this mystery particle that we want to put on here somewhere, and we want the total force on this third mystery particle due to gravity to be 0. All right? You good with what's being asked?
Yes,
So it's got to go somewhere in the middle. Can you tell me why? Yes. So if I put it in the middle, I'm going to just arbitrarily draw a little path. So here's our particle of mass 3m. How could that possibly have a net force of 0? Isn't it going to sort of? I mean, talk to me about why that net force would be 0. Okay. Yeah. I mean, it's going to be pulled equally in opposite directions, right? And so the question is, where do we put it, right? So,
You use the distance between x as a and the distance between n and 2n, or n and on x is a and n and 2n is d. So I got down to
well, d is a defined distance. The problem tells you this distance is d,
yeah.
right? So yeah, I mean, you need to give one of these a name. We can call it X, sure. Well, that might be confusing. We'll call it A. Then what should I call this? There you go, D minus A. Cool. And so the idea then is I want the force of gravity here to equal the force of gravity there, right? So let's color code this mess here. Oh no. No. All right, so give me an expression for this. So that green force of gravity is going to be G times and the black one is cool. So we set those two things equal to each other and solve, right? All right, well, let's see what happens. Does anything cancel? The M's go away. The G's go away. I'm going to flip everything over. I get A squared over 3 equals D minus A squared over 2, right? And then it's just a bunch of algebra and solve for A in terms of D. Dude, yeah. Yeah, hang on a second, let me take it up. Sorry, I don't know why I'm sounding. Chapter 13, question. What number is this? 4? Yeah. Okay, so if you. Oh shoot, I used R instead of A. There's no way I'm going to be able to. All right. So if you. Oh, gotcha. Sorry. Yep, I was just noticing that I had 6 here. Yeah, thank you. So it's 2m times 3m. Good. Sorry, I was blindly listening and not checking to see if you were right. So. Smart board. All right, so that's over 6. Did that work? All right, cool. So let's get rid of the fractions, multiply, so you get 6, 8. Well, here, better yet. What should I do? Yeah. Yeah, multiply by 6, you get 2a squared. There you go. Thanks. 2a squared equals d minus a squared is what? D squared minus 2ad plus a squared. Follow? All right, so if you set this all equal to 0, you get 0 equals a squared plus 2da minus d squared. I multiplied through by -1 because we were trying to solve for a, and I just like having the a as a positive. So then you use the quadratic formula, and if you use the quadratic formula, you get this: a equals -2d plus or minus the square root of 8d squared all over 2. And you can't have a negative distance, so it's got to be plus. And so if you simplify this, you end up getting root 2d minus d, which is the same as root 2 minus 1 times d. And that root 2 minus 1 is where I got the whatever the answer is on the sheet. So it's quadratic formula. I know I plowed through a lot there, Patrick. I know I plowed through a lot. If you take this and plug it into the quadratic formula, you get this mess.
Yeah.
Try that. And if it doesn't work, then let's talk.
No, I can screw it up.
Oh, gotcha. I hear you. All right, are we good, you guys? All right. And then Jacob, you asked about the 13? All right, cool. Am I going to see you tomorrow? Very enough.
Oh, no, I bet.
Okay, have a great time. Yep. 13. Oh, I'm so glad you asked about this one. So do you guys remember forever ago, we learned how to calculate the center of mass of different objects? And one of the examples I did was an example that looks really similar to this drawing. Right? There was a sphere, or I don't remember if it was a sphere or a disc or whatever, but there was a little chunk taken out. And I said that, so the first thing we did is we did it with squares, right? And I said, okay, to find the center of mass, here are your options. You can find the center of the mass of the chunks and then add them, right? And then I said, but sometimes you can't do that because there's no way I can sort of split this into chunks and easily find the center of mass. So I showed you how to do it by subtraction, right? Okay? Same exact premise behind this problem. Okay? We're going to use this subtraction idea. All right? So, all right, so what do we got? Number 13. You guys doing okay? Let me talk. Let's see. Figure to the right shows a spherical hollow inside a lead sphere of radius 4 centimeters. The surface of the hollow passes through the center of the sphere and it touches the right side of the sphere. The mass of the sphere before hollowing out was 2.95. What gravitational force does it exert? So, real quick, hypothetically, suppose that I had an object, and then some little mass, which we'll call m. Do you guys agree that I could find the net gravitational force on this by finding the gravitational force between these two and the gravitational force between these two and then just adding them? Does that make sense? Okay, and then if we move this over here, then you'd have to kind of subtract them, right? Okay, so that's kind of the idea here. But this time we've got, instead of having a sphere and another sphere, we've got a sphere and a anti-sphere, right? Like this negative sphere where we've got this hole cut out, right? So this whole surface, this whole sphere here is solid, but then we're missing this little bit here, right? And it's being attracted by gravitational force to this little dude over here called m. All right, so here are the numbers the problem gives us. It gives us this radius here is r, capital R. And then it tells us, doesn't it say that it's half the radius? It's been a couple weeks since I did this problem now. You trying to get ahead? Is it half the radius? Thank you. Are you guys excited that we only have one more chapter to do? I'm excited. All right. Yikes. That gives us more time to go back and get the things that we struggled with. So it's all good. Would you say rotation? Rotation, yeah. I didn't realize that you guys hadn't hit that last year. I feel bad. I would have done that differently. All right, so n is the mass. Notice this is before the cutout, right? Okay. Let's see. And then we know that this little mass over here is 0.431 kilograms. And I guess the last thing we know is that they are a distance of 9 centimeters apart. Is that what it says? 0.09 meters. Thank you, Tony. So let's write down our other numbers here. Let's see. We know that R is 0.04 meters. I think that's all given information. Half the problem is just writing out what you know, right? Okay. So, does anybody have any luck with solving this thing? Or ideas? Sure, what do you got, David?
Now, so if you do like the same thing, just solve for gravity between if the sphere was filled in, like the full sphere and the small sphere, and just subtract the gravity of the small sphere, so you get the gravity of like just the big sphere without the small sphere?
Yeah, that's exactly right. That's exactly right. So pretend that the hole wasn't cut out, okay? And find the force of gravity between the two spheres with no mass missing, okay? Then find the mass of this piece that's missing. And find what the force of gravity due to that chunk is. And then subtract it. So the question then is, how do we find this mass, this missing mass? You got an idea?
Your mass density volume of the sphere and then find density if you translate the density you can find.
That's exactly right. Hear that? He said from the original sphere, we know the radius and the mass, so we can find the density. And once you got the density of that missing bit, you can find the mass of the missing bit. Follow? right, so I'm not going to bog you down with the algebra. I hope you guys are cool with me kind of skipping some of the algebra?
Yes.
Okay, I'm trying to do more of that based on verbal and nonverbal feedback I've gotten from you guys. So here are the numbers that I've got for this thing. I found that the force of gravity from the whole mass, whole as in whole, not whole as in whole, that's not confusing, is, where did I write it down? Oh, I wrote a quick expression for it instead of figuring them out individually. Curse my plan to be efficient. How can I do this without going through all the algebra? All right, well, here, so let me do this. So that is going to be G times capital M times little m over d squared, yes? So that's from the whole mass, right? Right? Now, the next issue is the volume piece. So here was what I did. Do you guys agree that if I can find out what percentage of the volume this is, that'll also tell me the percentage of the mass? Makes sense? So let me do this. We'll go to a new page real quick. So the volume of the whole over the volume of the whole. Oh no, I'm sticking with this notation. There's no way we can get confused by this. All right, so this is 4/3 pi times capital R cubed, right? And this is 4/3 pi times R over 2 cubed, right? Follow? So what do you get? Everything cancels except for a 1/8, and you get 8. Follow? Oh, the bell.
This announcement is for boys track. Boys track, please meet in the whole athletic center lobby after school. Thank you.
I want to get some work done.
All right. So the mass of the missing whole is 1/8 of the mass of the whole thing, is what that boils down to. All right. And so then from there you just find your two forces, gravity and speed. Cool. All right. We are out of time. All right. So it sounds like most of you guys are going to be gone tomorrow. So for those of you who are here, we'll find something to do. Have a good break if I don't see you again. Why don't we make the last chunk of 13 due on not the Monday we get back, but the following Tuesday. Wednesday. Cool? Yeah. And then the extra credit is due the following Thursday. The due date for the extra credit? Sure.
How would one go about? I think I did something that was not against plan rule.